This is part 2 of solving code forces training on matrix exploitation. We will do problems GHI, and those are quite difficult problems, so this is not a video for beginners. I will not go into easy details. We will start with problem G, but before that we need to understand matrix exploitation a bit better. This is something we will use kind of in each of those 3 problems, and also its understanding of previous 6 problems as well. I will get in a moment what is associative property. But what we do with matrix exploitation is the following. We create some DP array, the initial one, and we multiply it by some matrix a lot of times, like k times or n times, let's say 5 times. And what we did so far is that instead of going from left to right, we here compute this, m to 5th power, and then once multiply by our array to get a new array, to get the final, because what we get at the end is dp final array. Okay, m is of size, let's say, s by s, this is of size s, this is of size s. Brute force would create this array, and then remember what we did, k times for every I, for every j, we did new dp of j plus equal dp of I times a matrix. This operation, those 3 lines, is to multiply array by a matrix, and the complexity is quadratic. But we can also multiply 2 matrices first. So this is in complexity of n square, s square, let's say that size of a matrix is s, but in complexity s cubic we can compute m times m with our 3 for loops. And to do that, instead of going from left to right, to do this, to gather those together, we use this associative property of whatever operation we have. It holds true if it doesn't matter what is the order of operations. If you need to multiply 3 numbers, like 2 times 3 times 5, you can go from left to right, but you can also put brackets, however you want. The same for adding. If you want to add 3 times plus 10 plus 5, it's okay to go from left to right to say 13 plus 5, 18, but it's okay to say this is 15 and then add with a 3. We want this from our property, from our operation. We do from this thing, this what we call product of matrices, but it's not always product. We saw that in problem about min path. Sometimes it doesn't hold, like even for numbers. If you want to subtract or divide, 10 divided by 2 divided by 5 divided by 2. If we go from left to right, we get 2 divided by 2, this is 1. But 10 divided by this is 10 divided by 2.5, 4. Okay, so it doesn't always hold true. Fortunately for you, you don't need to think if something satisfies associativity, if that's a word. You just need to think, can I combine 2 matrices into one? And that comes from statement. If we count paths, using some number of paths of some length and number of paths of some other length, can we combine that? And we don't think here about associative property. We just think, can I combine it? If it's reasonable, if you will figure out a way to do it, then it is associative. In any of previous problems, I didn't mention the fact, oh, now let's prove that this is associative, that we can do it. No, if you know that there are 5 paths of this length, 10 paths of that length, and you can combine them, you have 50 paths, and that's fine. You didn't lose any information. And we'll see various things in the next 3 problems. In one of them, for example, we'll deal with the fact that those matrices aren't all equal. And what do we do then? We cannot do binary exploitation. But that's the whole thing. Remember that we do this. Okay? Every matrix exploitation problem, almost every, is about doing that and just speeding up this part. Instead of doing n squared to compute that, then to multiply vector by matrix again n squared and so on. This is why brute force was s squared multiplied by the number of times we multiply. Okay, that's done. Let's move to problem G. We need to handle a linear recurrence formula with some twist, because every next element is the previous elements times something plus p plus I times q plus I squared times r. Without this is just like Fibonacci problem. But handling this is much more difficult. And we'll obviously start with just caring about P. By the way, stuff like that you can find in hints in Codeforce's article about this whole training thing. For every problem you should first look to that article for a hint, and only then watch this video actually. For a moment we'll assume that Q is 0 and R is 0, and we'll just handle this plus P. I already, here on the right, implemented a working DP solution. It has efficient space, O of n, but it's still linear, okay, where I iterate and every next element from n to k, after of course reading the input. I just simulate using this formula from the input, from the statement, sorry. And I compute new value, plus equal coefficient times that. I shift everything because I remember previous n elements. I should forget one element. So really all of that should be changed into something like that. I will not do it now because it's kind of boring. Oh, I even wrote it here as a comment. New dp of j is equal that. Yeah, we will do something like that for sure. No, we will do something like that for sure, because if I remembered previous, I have 3 values, 5, 8, and 4, and now I want to remember values 8, 4, and new computed value, because I remember let's say last 3 elements, then new dp of 0 is equal dp of 1, new dp of 1 equal dp of 2, and new dp of 2 is equal something complicated. So whenever I type here value, I just mean what, new dp of n minus 1, right? Yeah, looks so. This is just new dp is equal dp. I said that I will not do it now, so well, whatever. And I already created that. dp is new dp. I created here vector new dp of n. As you can see right now, I don't care about overflows and I don't care about value modulo. This is just, I'm working with dp in order to get proper coefficients to use matrix exponentiation, and I will use modulo and casting to long there. This is filled with zeros, but let's do this, or even this hack. By dp I mean a. Does it work? Yes, it does. Cool. I'm happy I didn't mess anything up. And this line is an issue. Everything else is cool. Well, here I mean this, but this is the same thing for us. Everything else is cool. We can do that into matrix, but we cannot handle that. How do we deal with it? It would be nice. Let's say for a moment that q is 0 and r is 0. Why I can't in any way put this into a matrix that I would compute a power of? Let's get back to this, where if I have a matrix, I multiply by it, I multiply my dp array by a matrix some number of times, I can compute this power. But this matrix needs to be the same every time. And the fact that here you have something like that you have this times I, and I is different every time, it means that this matrix is different. Let's say I is equal initially 7. This matrix is related to I equal to 8, and so on. I can compute matrix for one particular value of I, because for I equal to 7, this is a constant, maybe equal to 150. Okay, I can put it. The matrix can handle that. Well, we still don't know how, but let's say we can. Cool, but for next I, this will be different. I cannot compute some matrix to this power if this matrix is different every time. The product of 5 different matrices is not power of one of them. Okay, so that's our issue. We need to figure out one matrix such that we can multiply dp array of the same matrix by the same matrix some number of times, and then we're good. But we need to do that. Back. Okay, let's first handle any constant, like 150, just p, a fixed constant. I want to make this of form new dp of n minus 1 plus equal something times dp of something. Okay, this must be like that to handle p. And well, here I need a value. I can multiply 1 by p or p by 1, and that's it. It's not that I will use some random value here. So let's create a new cell. Let's say that dp of n will be equal to maybe p, just p, and every time it will be equal to p. So this will be dp of n and just plus equal 1. Okay, now we already have dp of size n plus 1. First n elements are just those initial values. dp of n is a constant. And I want to say new dp of n is equal dp of n. I just rewrite it. Of course, I could as well put plus equal. And now this is a bit bigger. I keep using dp, so let's at the end use dp of n minus 1. I cannot check anything now because I'm not handling I and I square so far. So this is a possibility. The other one, a bit more reasonable, is to here keep a 1. And you will see later that 1 is more useful. And this is then a 1, and now times p. I could put here, of course, a different value. Now the formula would be that every next element is 150 plus our normal linear recurrence formula like in Fibonacci. But we have p. Cool. How to deal with I? I don't want to use I from the for loop, because this should be independent on the current I. This basically should be just repeat some number of times from n to k inclusive, it's k minus n plus 1 times. Repeat this and don't use this variable rep. Initially just use I equal to n, then every next greater I. So let's try that. dp of n plus minus 1 plus equal a constant times I. How to get I? Well, it can be a variable. I will keep last n values, a variable always equal to 1, and variable I. What about that? dp of n plus 1 is equal, initially I need n, it's here. This is that, so this is just index, don't worry about that, but this is value I choose, and I looked here. The first I want to use is I equal to n. Then every time it will be greater by 1. Now you'll see why I needed a 1. New dp of n minus, I already have this line. This is dp of n plus 1. This is I. But I need to update I. So new dp of n plus 1 is dp of n plus 1, the previous I plus 1. This reads new I is equal previous I plus 1. Hence, I needed 1 for this. Of course, the order of those operations doesn't matter. New dp uses all dp. I could put this at the end as well. Sorry, what did I do? Cut this and put it here. This is fine as well. It's just here I update 1 and I use 1 and I to compute new element. That completely new element of big array A. Now the hardest term, I need I square. And let's use the same principle. New dp of n plus 2, so new I square, basically this, right? This is equal I square, and from basic formula from math, I know this. So this is equal dp of n plus 2, the previous I square, plus twice the previous I, plus 1. And that's the same formula. And I can now do this, plus equal r times dp of n plus 2. Not that hard after all. What's the initial value of I square? This, because this was the initial I want to use. dp of n plus 3, compile, and I think it's good. It's not good, out of bounds index. I forgot to change the size over there, and it's correct. Now it's not really nice to fix something like that. Maybe I should make a test with p equal to 0, q equal to 0, r equal to 0. I will try to figure this out just by looking at it. Oh, I have even better idea. Why won't I print dp of n, dp of n plus 1, dp of n plus 2. because those are some meaningful things. 1, 2, 4 makes sense, makes sense. This is indeed the last value is the previous one square. What should be the answer, by the way? 68 and 85. This is a complicated line, but obviously I should break it into new dp of n plus 2 is equal this, then plus equal twice that, and so on. This is all fine. It can be represented in the matrix. Oh, I think I know what's wrong. I didn't initialize dp at all. The first n values are just a of I. And 68, 85, cool. I don't need this. Okay, I think we're good. Just time to change this into a matrix. And before I apply matrix exponentiation, I will first just do this. Let's say temporarily n plus 3, this matrix. And I need to take all those coefficients in order to then just say for every I, for every j, new dp of j plus equal dp of I times the coefficient from going from I to j, dp is equal new dp. Okay, so time to maybe this I will create initially down there just to no, that's stupid, never mind. Okay, from n to n with coefficient 1. It's this. From n plus 1 to n plus 1 with coefficient 1, and just work it out line by line. From n to n plus 1, from n plus 2 to n plus 2, now it's tricky, n plus 1 to n plus 2 with coefficient 2. M of n plus 2 with coefficient 1. Okay, that's done. Can I remove it? Maybe better not. I will temporarily copy this above, because I don't want to scroll up and down. What do we have? From n to n minus 1, p, q, r. For every j, why not do the same for loop? For every j, move from n minus 1 minus j to n minus 1 with coefficient like that. And again, just make a for loop. I could reuse the one from the next line instead of rewriting. That's a bit stupid what I'm doing. I think I'm done. Everything else should be zeros. Whew. And comment out this thing. All the codes will be in my GitHub repository, so you can also read this if you need. What's wrong? I was not declared. I don't have my define. Define. Often, even though every day I don't use templates like that, in Matrix Exponentiation they are useful because in Matrix Implementation you really use a lot of for loops. Yeah, we are now good. Just time to put a matrix there and compute its power. Obviously, it's hard to come up with all of this just writing it line by line without going through the DP. But if you understand what happened, you can do the standard DP on a piece of paper and then just take coefficients. But it's quite difficult not to mess up. Still, if you do this for loop, you can check it by then printing every time dp of n plus 1, dp of n plus 2, just to see here if it was indeed 1, I and I squared. Or if you have computer and you have a lot of time, you can just first do this space efficient dp, make it to work on samples, and then take all the coefficients. And if you wonder, this formula could also involve I cubic, I to fourth power, and generally I to kth power, for k, let's say up to 10 or up to 50, and still one could figure out those coefficients. I don't know, maybe those are just binomial coefficients. Yeah, I think so. The next line of coefficients would be 1, 3, 3, 1. If we wanted to update I cubic using the previous I minus 1 cube. I will copy code from some previous problem. I have what I need. Struct matrix, the binary, how is it called? Binary explantation. I need just to choose this as after reading them. This is size of a matrix. Of course, you can do it better than creating global variable, but this works for me. What else do we have? Here, each of those lines should be turned into matrix.something. I don't want to rewrite all of that. Matrix single dot A of ij is of ij. If I created here a proper matrix, let's do it like that. Matrix total is binary explantation of single k minus n plus 1. I took this value from here. That many times I need to repeat. Let's compute the final, by new dp I mean final dp. New dp of j plus equal dp of I times total a of ij. Well, this should be with modulo. I want to get accepted. New dp of j plus this casted to long and a modulo. And I have my final array of variables. This is just a quick way to simulate everything that happened here. And print new dp of n minus 1. 0. Does it work? It does. Time to submit to make sure that I'm not showing you something stupid. Accepted with a nice time of 31 milliseconds. The complexity in this problem is quite small because size of a matrix is just 10 plus 3, so 13. It's 13 square times logarithm of this number. Oh, I didn't even remember that we have long That would be... I thought it's to 10 to 9, and if I rewrote this from scratch, I would get the wrong answer. Time to move to the next problem, string mood updates, or maybe you want to now try to solve it yourself, remembering about this thing, and I will give you some hint. Imagine a similar problem to problem H, where you have, let's say, n operations in a row. You want to make n operations in a row. Each one is one of two forms. Either plus something, let's say one is plus 6, here times 3. This is plus 2, plus 3, times 2, times 7, times 3, plus 1. Okay, you have such a sequence of operations. And if you have some initial value, like let's say 10, and you apply every next operation, you will get something like plus 6, 16, times 3, 40 something, and so on. And given queries about the initial x, you need to find the final value of x. How to do it? We can compress this a little bit. We can know that, well, I know that after, if I multiply something by 3 and add 2, let's say that we have just this. After multiplying any x by 3, I have this. Plus 2, I have this. Times 5, I have that. And so on. For any interval of this can be compressed into two values. For any initial x, I know that at the end I will have constant times x plus constant. Let's simulate it a little bit here. I will have x plus 6 times 3, it's 3x plus 18, times 2, this, plus 3, this, times 2, 46. times 7, multiply this by 7 and this by 7. So keep two constants, two variables, a and b, and whenever we have product, multiply both by this thing, and when you have addition, add something to b. Okay, and then at the end we know a and b. Likely everything is computed modulo billion 7, and we can answer queries. For given x equal to this, in constant time give me the final value after applying all n operations. And we can have updates. How to solve this problem if there is update? Change this operation from times 2 to plus 7. It can be done. You can pause the video now and think about it. 1, 2, 3. Segment tree. Segment tree often works with updates. For every interval here, with size being power of 2, like this thing and this thing, we can combine this like that. This will be a single node, something. I don't know how to mark it. This is some node. This and that is the next node, and so on. What a beautiful drawing I have here. Then this is also a node, and so on. Build a segment tree over those operations. In every node, keep those two constants a and b to say if a variable comes and goes through all vertices here, all leaves here, what will be the final value? And we can merge. If you know that this is segment that does times 5 plus 50, and this is does plus something, times something plus something, you can combine that. And this way, without thinking about our associative property, we anyway solve a problem. If you can combine, this is associative. And the same for our matrices. We will build a segment tree of items where every item, every node represents what I need to do with initial variable to have the final variable, to apply the transition. And in our problem, it will be a matrix. Here, this wouldn't be a matrix. It would be two variables, a and b. Well, constants in every node, because just two values. In our problem, we need 4 values. Happy to happy, happy to sad, and so on. In this problem, we have a string with letters and question marks, and each such character gives us a matrix of transitions, matrix representing transition for standard space-efficient DP, and we build segment tree out of that, allowing us to modify a single element, single matrix in a leaf of a segment tree, then update everything. Every time merging two children is about just doing matrix multiplication in cubic time, but it's just 2 cubic, size of matrix cube. And in the root, we have information about the whole sequence, which matrix we can now apply to the initial DP array. I think initial equal to 1, 0, just like in the problem B, string mood. We could also answer queries about interval of this string. If we are given a string like this and somebody asks us, what about this substring? We could also answer that. How many ways there are to replace question marks in this substring so that something would hold. Segment trees are quite basic, so I will not implement everything from scratch. I will just explain my implementation to you. Read the input. I have my base of my segment tree is a power of 2, so create that. For every leaf of that segment tree, you see every node of a segment tree is a matrix, 2 by 2. Initialize leaves of this segment tree, and I have function init that gets a character. Let's see it. Initialize given this character. There are some different ways to do it. My matrix is of size 2 by 2, and one of them would be to make a lot of ifs. Okay, if this is age, then the transition from happy to happy is Oh, apparently in this problem I used 1 as, sorry about that, I think it's different than in previous problem. 1 is happy, 0 is sad. Okay. Or maybe I will just use names. From happy to happy there is one way, from sad to happy there is one way, and for other things there is 0. For sad it will be the opposite. For a vowel it will be sad to happy one way, happy to sad one way. For question mark, and now for question mark you would need to work a little bit here to put all those numbers. I did it in a bit smarter way, where I iterate over all characters in the alphabet, and I say either if it's the same character with my given one, like H, or if the given one is question mark, so then everyone will fit, then I increase something by 1. This is a common technique in problems with question marks, with wild cards or wild something, wild card, where you iterate over all the possibilities. If it matches, then increase something by 1. And this is a nice way to do it. Anyway, create a matrix that would do something. Also, you can think about it this way. What if you just linearly go from left to right with dp? So for every next character, how to do it with space-efficient dp. Okay, and you need to, in some way, compute that matrix of coefficients for the transition. Okay, we can figure out the matrix for a single thing. And then we have something like that. dp array, the initial one with just 1, 0, times matrix 1, matrix 2, matrix 3, matrix 4, and so on. We build segment tree of that, and then we can quickly say what is combined matrix of this product, and we can modify one matrix. This will be now, update this to a new thing. Update everything in a segment tree on a path from leaf to root, and you're good. Let's see the whole code. For everything from end to base, it was convenient for me to put there such a matrix that it affects nothing. So in the root I would read the result. There are different ways to resolve that, but I could figure out either the matrix, or I noticed character Z or Z doesn't affect anything. It was set in the statement, so just if the string is this of length, let's say of length 6, add 2 characters Z, or imagine that they are there. Now it's power of 2, so it's convenient for a segment tree. Merge everything, where merging 2 children is about multiplying matrices, and every time I print root dot matrix of happy to happy. Every time I will print this. And yeah, I print this for every query, read the new thing, update the leaf, update path to the root. That's it. Code will be again in the GitHub repository. The last problem, and maybe the hardest one, count paths queries. We are given a graph, just like in one of previous problems, right? Yeah, there is count paths. A problem. Why is it scrolling to the right? D, count paths. Given a graph with 100 vertices, count paths of some length. And we can do it in n cubic times logarithm of k. Okay, but this time, and it's slightly bigger, it was just to fight with brute forces. And there are queries. And this time, for each of Q queries, if you do them independently, you get this complexity. And already Q times n cubic would be a lot. It would barely pass. Likely it would not pass if you have module operations, which are slow. Times logarithm, you have no chance. This is our brute force, maybe in quotes, because it's still, this uses matrix exponentiation. And we need, once again, to know what happens. We compute this, right? Let's try to do some pre-processing. I don't want to, a lot of times, compute the product of 2 matrices. In this problem, we will use the fact that multiplying array by matrix is a bit faster. It's n squared. And what if you were asked a lot of times about some constant number, a, let's say number 3, to big powers, 3 to 10th power, 3 to 15th power, 3 to something. How to slightly speed this up? When we write a binary exploitation, one thing is that we can remember everything we already computed. Let's not go into that direction because it's complicated how many times you will reuse a value. But for sure, always we use those values. It's convenient to remember those values. After once computing it, we can do it in logarithmic time. And now when somebody asks you about 3 to 10th, just multiply 3 square and 3 to 8th. So this we pre-process and remember. We store those values. In a similar manner, we have enough time to pre-process m to first power, m to m square, m fourth, m eighth, and so on. And the complexity of that is n cubic times log of k. We do that before queries. Now here's a final hint for you. You can pause after this hint, pause the video and think about the solution. Try to solve the problem without any more multiplying two matrices. Okay, it is possible because I don't want q times even n cubic. Even this is too much. I want this complexity plus q times something smaller. You can think how to, let's say, answer for k equal to 3 or k equal to 6. So this, for example, k equal to 6. I want to compute this, right? I want to compute dpri times m squared times m to fourth. And now in 5 seconds I will tell you the final solution. Just go now from left to right. Multiply Ri by a matrix you already computed, and we do that in n squared, and so on and so on. What do we do with 15? With 15 we have this, or let's say 32 instead of 16. I increased by 8, so this is what, 23? Yeah. K equal to 23. How to solve in complexity O of n squared times log of k? Just go from the left. So 23, no k in binary representation, represented in binary format. This way you know which bits you need, so which exponents of m you need, those preprocessed ones, and just move from left to right like in a brute force manner. This takes exactly that complexity. So the total complexity is n cubic times log of k, plus that was preprocessing to compute this. For every query, we combine that many matrices, but instead of multiplying them with each other, we just go array times every next matrix. We never here multiply with each other two matrices. By the way, there's one more idea you could investigate, but it's not fast enough here, is pre-compute square root of n, square root of k first matrices, or something like that, where you compute m to first, m to square, and so on, m to some square root, and then once every square root you also pre-compute that matrix, then you can actually answer here in constant time instead of log of k. You can think about it, but it's not faster, at least not in this problem. I will again just show you the solution, I guess. There is nothing crazy going on here. In very short, what happens is I create the single matrix, I pre-compute 30 powers, and after that I want to know the binary representation of k. If this bit is on, then update dp to be new dp with 2 for loops. This is quadratic time. In a moment I will show you one smarter implementation of this, because multiplying two matrices is quite similar to multiplying vector by a matrix. Actually, vector can be treated as a matrix of size n by 1. And those two things can be done in the same code. I saw that in one of participants' code. I sorted by submission time because this was the first correct solution to this problem after 2 hours of the contest. Nikola Pesic, congratulations. And he has function multiply given two vectors of the vectors, so two-dimensional arrays of size, they must be of size a times b and b times c. The second dimension of first matrix must match the first dimension of the second matrix, or something like that. And then you can make 3 for loops, and just that if one matrix is of size 1 by something, this will be quadratic instead of cubic. You can analyze this code, or you can go to submissions, sort by time, and open his code. I think that's quite smart, because it's shorter than my code, where he creates the initial matrix, he creates those powers, and then the same thing I have here, he has there, plus he uses the multiplication again, both for multiplying two matrices and multiplying vector by a matrix. So, you know, I learned something new as well while checking solutions of participants to this contest. In general, congratulations to everybody who solved all the problems. I saw a lot of red people also just solving some suffix of problems. And indeed, for somebody yellow plus, it will be beneficial only to solve those 5. Or maybe to experiment a little bit with the speed of your code, you know, with stuff like, what if I change the order of for loops here? If you change actually those 2 for loops, or some of them, the running time will be much slower. There's something called cache, being cache friendly, where you want your last for loop to be only the last dimension of things you use. So here, having, for example, j as the last for loop would be bad, because I'm here very not cache efficient. It's bad to jump over this. If you Google code forces cache in two-dimensional arrays, you can read more about it. I think this is everything. Thank you for watching, and thank you everybody for participating in this contest. I'm glad that a lot of people tried those. What do we have? Yeah, we have 500. In the first problem, some people just retype my solution from the very first video about matrix exploitation. But for other ones, really people just solve those problems. I'm cool with such number of participants. I will try to do something similar in the future, maybe with some help from the community, like not to prepare all the problems myself. Well, still, this wasn't my problem. This was by Tomek Nowak, Recurrence with Square, though I knew already such a problem. Okay, codes are in the GitHub repository, link in the description. Bye bye, subscribe.